speaker is Professor Keiji Saito from Keio University. Before starting his talk, let me briefly introduce Professor Keiji Saito. Professor Keiji Saito received his PhD from Osaka University at 1999. And at the same time, he got a post as an assistant professor at the University of Tokyo. And 2012, he moved to the Keio University. And now he is a full professor of Keio University. And he has been very actively working on the research field of non-equilibrium statistical mechanics and quantum many-body dynamics. Actually, he received honor of Ryogokubo Prize at 2016. And now he's going to tell us about information dynamics in the long-range interacting systems. So Saito-san, please.
Yes, thank you very much, Okumi-san. I'm Keiji Saito from, can you hear me, by the way?
Yes, sure.
Okay, so I'm Keiji Saito from Keio University. I'm very happy to be here, getting the opportunity to give a presentation of our studies. I'd like to thank all organizers of this project. My talk is about the dynamics of information propagations, and the title is divided into two parts. The study in the first part is done with Kuwahara-san from RedChem, and the second part was done with these people. The first person, Minato-san, he was a student of mine, and he is now in company Hitachi, and Sugimoto-san, who is the assistant professor in Keio University, and again Kuwahara-san in RedChem. So as Okumi-san said, I'm a statistical physicist. My field is non-equilibrium thermodynamics and also quantum dynamics and information also. But I think many people in the audience here, it's part of a different field from mine. Terminologies and the way of thinking and so on may be different from mine. And so you can interrupt my talk whenever you want. So this is the plan of my talk. My talk is about information dynamics in the long-range interacting systems. So before going to the main part of my plan, a little bit make a remark about the system that we are thinking about, and also terminology is remarked, and especially I want to remark about the difference between the short-range and the long-range interacting systems. So we are thinking about the dynamics of many-body systems. The short-range systems are very common in condensed matter physics. The example includes Heisenberg model, which looks like this in the Hamiltonian. Interaction exists only between nearest neighbors. On the other hand, we talk about the dynamics in the long-range interacting system. In my talk, long-range means power law decaying system, whatever the exponent is. Keep in mind the exponent alpha here. In my talk, I always use this alpha. In the conventional terminology in the statistical physics, long range means the case where alpha is less than spatial dimension, but we don't care about this strict definition of the long range systems. The example like this. So long-range interacting system has been one of interesting targets in the statistical physics. And so many interesting properties have been known in the thermodynamics. For example, when alpha is less than spatial dimension, additivity in the thermodynamics is violated, and this can lead to violation of the concavity of thermodynamic entropy. And this leads to another non-trivial phase function and so on. So I do not explain much on this because I want to focus on the information propagation in the long-range interacting systems. So here I want to emphasize that long-range interacting systems are rather ubiquitous in nature. Of course, you know, in nature, there are many kind of power law decaying systems. Example includes the gravitational field, of course, and another important interaction is magnetic dipole in the magnetic system. So these are very common in a sense. So what I want to stress here that recent experiment and technique can tailor the interaction form and also interaction range. Here is an example of the experimental picture using the ion trapped system. This system realized the Hamiltonian looks like this. This is a long-range Ising model. Very interestingly, even global coupling can be made. This type of experimental direction have been believed to have a potential to provide laboratory experiment to consider something non-trivial, including black hole physics and so on. I do not know the state-of-the-art experiment in this direction, but anyway, very interesting direction. So let's start the first part. In the first part, okay, so let's start the first part. But before that, I must remark about the information. As I said many times, my topic is the dynamics of the information. So remember that my topic is information dynamics in the long-range system. So the question is what is the information actually? Information is a very rather ambiguous terminology in my feeling. So information theory, information is characterized through channel entropy, and channel entropy quantifies how rare the event is. In quantum information theory, we sometimes talk about entanglement entropy as information. In our talk, information, or more specifically, information dynamics means operator splitting in the first part of my talk. Because any information can be propagated through operator splitting. Operator splitting is the following. Let's think about the time evolution of OXT. OXT is a Heisenberg picture. This can be expanded like this. At time t equals 0, OX is defined on the side x, which is a local operator. But as the time is elapsed, higher order correlators are needed in the time evolution. And so the operator becomes non-local. And this means that operator is split in the space. In the first part of my talk, we focus on the operator splitting. And in the second part of my talk, we think about the more specific information dynamics, namely the dynamics of entanglement. So I explained the second part. The image of the dynamics of entanglement like this. Okay, so this is a very introductory part of my talk. So let's start first part of my talk. So as I said, we think about operator splitting. Actually, this topic has a connection to the black hole physics. In the black hole physics, well-known information paradox has been one of important subjects. In the study of information paradox, information scrambling is very critical to understand what occurs in the dynamics. Suppose that information starts from the origin. And suppose that, and we consider the time that information reaches at the radius r. In this case, we have mostly three cases. There are mostly three cases to classify the time that information reaches. The first class is a case where T reach is the order of R. In this case, we expect that light cone exists in the information propagation. The second case is a case where T reach is a order of R to the power Z, and Z is larger than 1. Even this case, we still expect light cone, but the light cone is nonlinear light cone. And third case is a case where T reach is the order of logarithmic of the distance R, or faster than this. In this case, we call this fast propagation. If you think of out of time order of correlator, this regime is called fast scrambling. But I use a more moderate terminology, fast propagation, because I don't necessarily use OTOC in my talk. Okay, this is a classification of the operator splitting. So keeping in mind this classification, I explain the function that we consider to characterize the operator splitting. The target function is this. And OX is the operator defined at the site X. And similarly, OY is the operator defined at the site Y. And this is a commutation relation. We use Schatten P norm, and P norm is defined mathematically like this. At time t equals 0, OX and OY is commuting, and so this function is 0. But at the time is elapsed, operator OXT becomes non-local because of the operator splitting in the space. And at the long time regime, this function becomes finite. Like this function is very nice function to as an indicator of operator splitting. So we put P norm here. Usually we have two classes of the target function. One choice is P equal infinity, which means an operator norm in the norm. Operator norm gives the target largest eigenvalue, and so the function provides the fastest information propagations. Imagine the following situation. So in general, there are many kinds of information propagation. This propagation is slow. This information propagation is fast. And this is the fastest, like this. There are many kinds of information propagation. This operator norm detects largest value. Even at this propagation is 0, but this propagation is finite. So the P norm, P operator norm detects the fastest propagation. Like this, the operator norm detects the fastest propagation. It's okay. Okay, so another important choice is P equals 2, which is a Frobenius norm. This case is equivalent to the out of time order of correlator, OTOC. This is written like this, like this. And so this means that the function is expectation value for the infinite temperature density operator. So this is it. This is 1. So this means infinite temperature density operator is here. Then this means in OTOC, many propagations are averaged. This propagation and this propagation and this propagation, all type of propagation are averaged. So the OTOC provides typical information propagation. So physically, operator norm expressions and OTOC expression provides a bit different physics. Operator norm case provides a fastest propagation, and so we expect that this provides a kind of fundamental limitation of the information propagation. Okay, this is a very important classification of the target function. So let's move on to the next page. Now we focus on the operator norm version of the information propagation. In the information propagation, the most important work is the Lieb-Robinson bound. Suppose that we think about the short-range interacting system like this. Then the example is the Heisenberg model with the nearest neighbor interaction. Lieb and Robinson derived the following important expression for the bound of the operator splitting. This bound is schematically drawn in the following diagram. This means that for the regime with a large distance, the information propagation is exponentially small. And this is the light cone in the information propagation. And V is sometimes called Lieb-Robinson velocity. And V is very important. And the Lieb-Robinson velocity is roughly estimated by the order of the amplitude of one side interacting operator. Okay, this estimation is very reasonable because the operator splitting occurs locally, and so the one side local Hamiltonian should be a driving force. And so the Lieb-Robinson velocity should be the order of one side energy, one side interacting energy. So keep in mind this dependence. I use this in the later discussion. Okay, so now before going to the main part, here I want to a bit mention on the importance of Lieb-Robinson physics. Actually, this page is not the mainstream of my talk, but I want to mention the importance of Lieb-Robinson physics. So the Lieb-Robinson gives the limitation of the causality, in a sense, causality. So causality is definitely important. So fundamentally, Lieb-Robinson bound is very important. In addition to this, I want to stress that Lieb-Robinson bound has a lot of applications leading to the non-trivial, crucial, and universal physics. For example, using the Lieb-Robinson bound, we can show that the property of in the gapped system. Gapped system means that the system has an energy between the first excited state and the ground state. This type of system is called the gapped system. In the gapped system, any two local operators with a finite distance shows the exponential decays in the correlation function at the ground state. This is a universal properties in the ground state. This universal properties can be proven using the Lieb-Robinson bound. This is a very interesting application because Lieb-Robinson bound is a physics in the time domain. But the exponential decay at the ground state is a static thermodynamics. So the non-trivially time domain physics can be applied to the static thermodynamics. It's a very interesting application. So like this, there are many applications. I do not say much about the application, but this should be something to be mentioned anyway. So now, let's go to the main topic. So now the question. So far, I explained the information propagation for the short-range interacting systems. A short-range interacting system. So the question is the following: what is the effect of long-range interacting, long-range interaction? So to this end, let's think about the following long-range interacting systems. The setup is the following. I and J are index of the lattice, and Hij is the interaction between the side I and side J. We assume that the operator norm of Hij is less than this quantity. And here, Dij is the distance between side I and side J. Okay. The example is like this: long-range Heisenberg model like this. So then the question is the following. Background of the question is the following. Long-range interaction system. Long-range interaction instantly transfers the information to the distant location. But on the other hand, the amplitude of long-range potential is small for long-range distance, large distance. So what is dominant? That is the question. What is the dominant between these? And what is the condition to get the linear light cone? This is the main subject that I want to address. Okay, so for this page, I want to use time a bit, and I want to show the hand waving argument to get the condition to get for linear light cone. So to get the feeling about what occurs, we should understand the role played by the short-range interaction and the long-range interaction, respectively. To discriminate the dynamics arising from these two types of interactions, I divide the interaction into two cases. One is the short-range dynamics, short-range interaction, and another is the long-range interactions. H short is a part of short-range interaction, where range of interaction is up to the distance L, small l. H long is a part of long-range part, where the range of the interaction is larger than L, okay? Schematically, you can see this graph. Then what we want to understand is the properties of the dynamics given by this guy. But this is not different from the original unitary time evolution. Still, it looks difficult to analyze. So as a first step, let's think about the similar but much easier dynamics to get physical feeling, namely the product of the time evolution. The first term is e to the minus I h short t. This should give the standard Lie Robinson bound. This dynamic should show standard Lie Robinson bound in this form. Okay, and the question is about the second term, which is the contribution from the long-range interaction. This term is expected to give this type of Lie Robinson bound. And V prime is a term arising from the short-range Lie Robinson picture using the amplitude of one side interacting operators. So as I said in the several previous page, Lie Robinson velocity is the order of one side interacting operators. So using this picture, we can calculate V prime even for long-range interaction systems. But the range of the interaction starts from the distance L, okay? So the propagation should be L times faster than the short-range picture. So I multiply V prime times, I multiply V prime by L in this term, okay? This is the reason why I put this. Now we estimate V prime from the criterion that Lie Robinson velocity is given by the amplitude of the one side interacting energy. So this is a rough calculation. Calculation is very easy as long as it's rough and straightforward. And eventually you get this term L dependence. In the end, you can get the effective velocity like this. Effective velocity is V prime times L, and this depends on the L times the power d minus alpha plus 1. Okay, this is a rough estimation using the this product type of time evolution. What does it mean? This means if alpha is larger than t plus 1, then this effective velocity arising from the long-range interaction becomes zero as increasing L to infinity. So this means if this condition is satisfied, this long-range contribution is negligible compared to the short-range time evolution. So the long-range contribution vanishes and the linear light cone arising from the short range appears. Then like this, if alpha if this condition is satisfied, the linear light cone is expected. So this is a kind of exercise using this product type of unitary time evolution. So now, let's think about the true dynamics. True dynamics is this. And the question is what's the effect of long-range interaction? So actually, for this time dynamics can be product form in this way using the interaction picture. So this H long S is given by this interaction picture, and here left arrow means a time ordered product. Because of time evolved operator, this is already non-local operator, and non-local operator have to be treated, and we have to estimate the one-side interacting operators to estimate the effective reproduction velocity arising from the long-range interaction. As estimated in the previous page, when t equals 0, one-side interacting operator is the order of L to the power d minus alpha. But for finite time t, because of the time evolution, the operator ballistically expanded in space. So the rough estimation for the amplitude on the one-side interacting operator should be different from this, and roughly impose the term of the ballistic operator splitting. This is a very rough estimation of the operator splitting in the amplitude. So in this expression, V prime times L is estimated like this. And let's dare to replace T by L. Then the effective velocity in the long-range interaction is estimated by the L to the power 2d minus alpha plus 1. So suppose this is correct, then the condition to get the linear light cone arising from the short-range interaction is given by the alpha larger than 2d plus 1. In this case, the long-range term is negligible compared to the short-range contribution, and then we get the light cone.
Sorry, is it okay if I ask a question?
Okay, yes, of course.
Yes, so in number 2, the first line, I didn't understand, are you assuming that this decomposition holds as a generalization?
This is the exact expression. Interact with interesting picture. Interaction picture.
I'm confused. If the Hamiltonians don't commute, why would Why would this
Yeah.
equal?
It doesn't commute. So this is given by this.
Oh, I see. I understand now. Okay, thank you.
Yeah, it does. Sorry, I didn't explain much on this. So this is a formal products, formal decomposition of from H short and H long. But this time also includes the contribution from short length, H short. Okay, so this contribution already has the time evolution, and this is already non-local operator because of the time evolution. So we have to take account of the non-local contribution. And to account the non-local contribution into the deprovision velocity, we roughly multiply this guy by t times power d because of the ballistically operator splitting. So using this and replacing t by L, then we get this type of effective velocity. This is a very rough and hand-waving argument. I don't know if it's correct or not at the moment, but it turns out this is correct. This is rigorously exact with rigorous calculation. So this is a hand-waving argument. So now, from now, in this page, I show you the state-of-the-art classification for the operator norm version of operator splitting. So we can show rigorously the following the diagram of the operator splitting. As roughly explained, linear light cone for this regime is shown. This regime is the case where alpha is larger than 2t plus 1. And we can show that as long as alpha larger than 2d, a light cone exists. And for the regime where alpha is between 2d and 2d plus 1, we can show the bound of the information propagation is polynomial light cone, like this. On the other hand, if alpha is less than 2d, the bound shows the fast propagation. The fast propagation means this dependence. The time that information reaches is a logarithmic of the with respect to r. And for shorter, so this regime is a fast propagation, is a information propagation.
Keiji,
So
can I ask a question? Sorry, can I interrupt? Yeah, so yeah, when you say linear light cone in this long-range system, of course, as you said, there is an instantaneous power law propagation whenever, because the Hamiltonian contains long-range term. So what do you mean by this linear light cone? So you say that there is an upper bound of this form. It's exponentially decaying in R. So
yes, this is the expression for the asymptotic result. R have to be very large. In this case, the long range contribution negligible can be negligible because of the amplitude of long range interaction is very small compared to the short range contribution. In this way, we can think that linear light cone.
Oh, but this is, but I don't know. So, but if R is large, this, of course, this exponentially decaying. Okay.
But VT can be comparable to the R.
Okay. So you say that there is a region when this upper bound is correct, this exponential factor is not too small, and this parallel trivial part is very, very small.
Right. Yes.
Yeah. Thank you.
Yes, thank you. So this is a state-of-the-art classification, and the comment is thank you for comment. And and this is a rough diagram. And you may be interested in the OTOC case, which is a Frobenius norm. And maybe the OTOC is more relevant than the operator norm case in the black hole physics, I guess. there are many unclear things on the OTOC at the moment. But recently, we recently showed that kind of no-go theorem that fast scrambling is prohibited for the regime of alpha larger than D. So in statistical physics, it's well known that the case alpha than D means thermodynamically stable, meaning that the extensibility and additivity and the concavity of thermodynamic entropy and so on are satisfied. So in the thermodynamically stable system has light cone in the OTOC. This can be proven, but we don't success at the moment. We don't succeed in the linear light cone in general. So a lot of things are not clear at the moment. And you may be familiar with the spike model, such Deffier type model. This sits on the alpha equals 0. This case, as you know, this shows fast scrambling in the OTOC. The people believe that alpha less than D means fast scrambling, but I don't know at the moment. So this is a rough story about the first part of my talk. So before going to the second part, if you have a question, I accept the questions or comments.
Can I ask a question?
Of course.
In the case of quantum field theory with local interactions, is this same as the limit of alpha goes to infinity?
Alpha goes to, actually, at the moment, we are thinking about spin system, and the operator norm is limited at even at the local site, and so we have to separate the argument between the fermionic system and bosonic system actually. But if you think about the fermionic system, the usual field theory is short-range interacting systems. If you think about the short-range interacting systems.
Why does the statistics matters?
Why
does the statistic matter? Whether fermion or boson?
Actually, yeah. Actually, I didn't say about this actually at the moment. Actually, the information propagation actually highly depend on the statistics, because suppose boson enters one side, many boson enters one side, then because of large interaction, information can be faster because of the large interaction of the bosonic system. But in fermionic system, the interaction is very small because of the Fermi's exclusion principle. So as I said, remember that the Lie Robinson velocity is the order of the one-side interacting operators. In bosonic system, boson can enter the one side at the same time, and so the interaction can be very large. So the Lie Robinson velocity can be very large in the bosonic system. So the physics can be different from the fermionic version.
I see. Thank you so much.
Yeah.
Ask a question. So in the long range system, we often have some thermodynamical instability, something like, for example, negative specific heat and so on.
Yeah.
Is this kind of instability related to this kind of transition, or it's far from that?
I think it's a very interesting question. The answer is not clear to me. As long as OTOC, it seems to be related to thermodynamics, but I don't have no proof between the connection at the moment. Yeah. The operator norm quantifies the fastest information. So it's a bit different from thermodynamics. But as I said, OTOC is the average of the information propagation, which looks like the average over the thermodynamics density operator. So it looks similar, but I don't know the connection between them.
Thank you very much.
Very interesting question. Thank you very much. So if you have no comment or questions, let me move on to the second part of my talk. So far we have seen the operator splitting, but from now on, we focus on the entanglement propagation. To this end, we first must define the entanglement. Suppose that we have pure wave functions spanning regime A and B. Then we compute the reduced density matrix like this, and we compute the von Neumann entropy like this. If wave function is the product state between A and B, then this gives 0, but this gives a finite value if the wave function you are thinking is entangled state. This is an example for the singlet state. You get finite value. This is the definition of entanglement. Okay. So as we considered so far in the first part, the operator splitting have a linear light cone if the interaction is short range. And so we usually expect that entanglement also grows linearly in time if the system has short range interaction. This is in fact true in general. For instance, suppose we are thinking about suppose we have many body interacting systems such as transverse Ising model like this. When we start with the product wave function like this, all up state is a product state in the wave function. And what happens in the entanglement in the time evolution like this? So to consider the entanglement, we divide the system into A part and B part, and we consider the time evolution of the entanglement entropy. The typical entanglement growth looks like this as a function of time. Entanglement grows linearly in time and eventually saturated. And the saturated value is the order of system size. This picture is rather very common in the pure quantum dynamics. So the important message from this is that the pure quantum dynamics makes the entanglement to grow up to the system size. Okay, so this is one thing. And now, next I want to explain about the quantum measurement. In spin systems, typical quantum measurement measures local spin state. So if the singlet state is prepared, and after the quantum measurement, the output is either up, down, or down, up. And so the output state is a product state. This means that local quantum measurement kills the entanglement. So this quantum measurement is a new keyword in my talk, and so the message here is that quantum measurement is a source to suppress the information propagation. So yes, so the quantum measurement is a source to suppress the information propagation. This is a message from this page. So from these 2 pages, I have seen 2 aspects. One is the enhancement driven by the pure quantum dynamics, and the saturated value is the order of system size. And another aspect is from the quantum measurement, and the quantum measurement suppresses the entanglement growth. And there is a competition between them. Suppose that we make a quantum measurement with a frequency gamma, like this. And then what occurs in the entanglement growth? because of this competition. So very interestingly, there is a phase transition between them. There is a critical frequency gamma C. Above gamma, a quantum measurement is dominant, and so quantum state has small entanglement, which is order 1. But in the small frequency below gamma C, pure quantum dynamics is dominant, like this. And so the quantum state has a large entanglement, and the entanglement is the order of system size. And this is a critical point. This type of dynamical phase transition occurs. And this phase transition is called measurement-induced phase transition. So this is very interesting recent development of the entanglement entropy. So this phase transition has been discovered just 3 years ago. The first paper uses a quantum circuit like this. I don't explain much about the quantum circuit is, but you can imagine this type of circuit. This is type of quantum gate. They put quantum measurement with the probability P, either here or here or here, that you make a measurement with the probability P. So they demonstrated that following left figure. Left figure demonstrates that the two different initial states, two different initial wave functions show the same saturated value of the entanglement entropy in the long time limit. For example, the different line is a different measurement frequency, measurement probability. For example, this blue line, they start with this initial condition, and also they start with this initial condition. Two initial conditions eventually go to the same value in the entanglement entropy in the long time limit. So from this, we get the information that the entanglement entropy is saturated in the long time limit. Believing this, we estimate the long time value of the entanglement entropy at large. Yeah. So let's see at the final time here. The different curves are different measurement probability. Okay, and there is a critical probability PC. Okay, there is a critical probability of measurement PC. Below PC, entanglement is large, which is the order of system size. Above PC, no growth in the entanglement occurs, and the saturated entanglement entropy is order 1. Okay. So this is the indication of the phase transition. In addition, yes, we call this phase volume low phase, and this phase is called area low phase because this is the volume. This case shows the volume dependence, size dependence in the entanglement entropy, but this case shows the entanglement is order 1, so we call area low in this case. So in addition to this indication, they showed the finite sign scaling like this in the entanglement entropy. So from this, they concluded that this phenomenon is rarely phase transition. And I want to also mention that recently one experiment exists on this. But actually, I'm not familiar with this experiment, so don't ask me the detail on this. So anyway, many studies exist on this measurement.
Keiji, I'm sorry.
Yeah.
What did you say about this finite site scaling? Does it suggest that this is a second order phase transition or?
Yes, this is a second order phase transition. Yes.
Oh, okay. So at this critical value, okay, you see this critical behavior of disentanglement.
Yes, right. Yes. So this size dependence is a typical finite size scaling for the second order phase transition.
Oh, yes, yes, yes. Okay, thank you.
Very interesting analysis. And actually, you know that measurement is a kind of infinite temperature heat bath, a kind of the infinite temperature dissipation, as you know. So if you think about the density matrix in the long-term limit is the infinite temperature density matrix. It's a kind of identity. So as long as you see the density matrix, nothing happens. But if you look at the wave function, this type of phase transition occurs. So this is very interesting thing. So usually physicists think about the density matrix physics. But if you look at wave function has some information, and this shows the phase transition. It's a very interesting aspect. Okay, so in the natural context of my talk, I want to raise the following question. What is the effect of long-range interaction? Very trivial question from my stream of my study. So what is the effect of long-range interaction? So the background of this motivation is the following. But as we have seen in the first part, long-range interaction enhances operator splitting. So this indicates that entanglement growth should be affected by the long-range interaction. So the question is, what is the effect? What is the effect in the measurement in this phase transition? Because entanglement is enhanced by the long-range interaction. Okay, this is a natural question, I think. So, because of lack of time, so we make a state of our result. Our finding is the following. Our finding is on the sufficient condition to get the existence of measurement-induced phase transition. The sufficient condition to have the phase transition is given by the following criterion. If your system is a non-interacting fermionic system, then the sufficient condition to get the phase transition is given by the alpha is less than d half plus 1. D is a dimension, special dimension. And if your system is general means non-integrable system, non-integrable d-dimensional system, then the sufficient condition to get the phase transition is given by alpha is larger than d plus 1. So let me explain roughly about the background to derive this statement. The background is very simple, actually. So this is the exact formal expressions of the entanglement growth rate under the pure quantum dynamics. So note that this expression is for the pure quantum dynamics without measurement. We don't care about the measurement, and we want to estimate how large the entanglement growth is in the pure quantum dynamics. So here, HAB is defined in the following way. So originally, the Hamiltonian looks like this. Hamiltonian is decomposed into the three parts. What is HA and HB and HAB? HA means the interaction is within the regime A. And HB is also the Hamiltonian part where the interaction is only within the regime B. HAB is a Hamiltonian part bridging between regime A and regime B. So this type of Hamiltonian appears in the entanglement growth rate. And so this Hamiltonian is very important. We call this Hamiltonian boundary Hamiltonian. The boundary Hamiltonian is a key role, has a key role in the entanglement growth rate in the dynamics. If the entanglement growth Okay, so if the entanglement growth rate is pure in the pure, sorry, if HAB is finite, if boundary effect, the operator norm of the boundary Hamiltonian is finite, then this indicates that entanglement growth rate is finite. So in this case, if you make very frequently, strong frequency in the measurement, then the measurement can beat the entanglement growth rate from the pure quantum dynamics. Then we expect measurement in this phase transition should exist. On the other hand, boundary Hamiltonian, norm of the boundary Hamiltonian becomes infinite in the thermodynamic limit, then any finite large frequency in the measurement cannot beat the entanglement growth from the pure quantum dynamics. Then in this regime, we don't expect measurement in this phase transition. Okay, this is the rough story. And then from this criterion, we can derive this sufficient condition to get the measurement in this phase transition. In the next two slides, I show a numerical demonstration that the criterion works well using the specific model. The setup is the following, using this Hamiltonian. Hamiltonian is very simple, in a sense artificial because of this. But anyway, this is a bit tractable model to consider what happens in the numerical calculation. Then I use this. Because of lack of time, I show the numerical calculation for only for free variable systems, setting V equals 0. In the dynamic, concerning the dynamics, we use quantum jump process with quantum measurement. This is called quantum trajectory. And we make a quantum measurement on the particle on each side. We detect whether the particle exists or not. And after the measurement, the state is projected onto the measured state. And in the dynamics, W takes 0 or 1 with a Poissonian process. If W equals 1, then the quantum measurement occurs. And otherwise, pure quantum dynamics is performed. This is the dynamics. So in this case, we measured the number of particles on the site, or each site. Okay. So with this dynamics, we can demonstrate that our criterion works well. And this is a typical result of the saturated entanglement as a function of L. If alpha equals 2.3, order 1 inter-entanglement entropy and size-dependent regime are separated. And so we expect that there is a phase transition in this regime if alpha equals 2.3. On the other hand, if you set alpha to 0.8, then the entanglement entropy in the long time limit depends on the size. This means order 1 area of phase doesn't exist. Then no phase transition occurs here. The phase transition should be related to the correlation between the two places, usually. So we computed mutual information between the regime A and regime C. And definition looks like this. Mutual information A and C is given by this. And SA is a von Neumann entropy for the regime A. SAC is a von Neumann entropy for the regime A plus C. Like this, you can calculate the mutual information. And the mutual information quantifies the correlation between the regime A and C. So all information are involved in the correlation. And if you calculate the mutual information as a function of measurement frequency, you find this type of structure. And in fact, this crossing point indicates the critical point. So believing that this is a critical point, you can plot the critical point as a function of alpha, like this. So as you see, below alpha equals 3/2, no critical point exists. Above 3/2, the critical point exists here. This is consistent with our criterion. In our criterion was that if alpha larger than 3/2, free fermionic system shows phase transition. So this is a consistent. Okay, this is a second part of my talk, and let me summarize on my talk. In my talk, information propagation is considered especially in the long-range interacting systems. In the first part, I explained the operator splitting, and operator splitting, especially the operator norm version, is classified. And as I said, the OTOC version is still unclear, and many interesting questions exist. In the second part of my talk, and in addition of growth, but the suppression of entanglement is considered, and I showed, I told you about the measurement-induced phase transition. And we provided the general criterion to observe the measurement-induced phase transition. Okay, that's all. Thank you very much for your attention.
Thank you very much for great talk, including the information propagation and measurement-induced phase transitions. So now it's time for question.
Can I ask a question, Saito-san? Hello,
Yes.
Can you hear me?
Yes.
So my question is related to the second part. So you mentioned about the measurement-induced phase transition. So I'd like to know the relationship, the measurement-induced phase transition and the quantum Zeno effect. So
yes.
So this is a kind of a quantum Zeno effect, right? But
Yes.
so I'm wondering, the choice of the measurement base is very sensitive to this phase transition. So you now perform projective measurement for each site, right?
Yes.
So you always take the same measurement, okay?
Yes.
If you change the basis of the measurement for the half part of the system, then so I expect some anti-Zeno effect. So by changing the measurement operator, then and you perform repeatedly such an additional measurement operator, then the dynamics change drastically. So I just guess you may have such another dynamics like anti-Zeno effect that implies the usual quantum Zeno implies that the speed of the change is small. But if we have such anti-Zeno effect, the speed of change becomes faster. So it may be interesting to change such a basis of the measurement. What do you think about that?
Yes, very interesting question. Yes. So concerning the first part of your questions, this phase transition is highly related to Zeno effect, of course. So if in the limit of the high frequency limit, this shows Zeno effect. And in a sense, the phase transition is a phase transition between the volume law phase and the Zeno transition phase. And so you're correct. And concerning the second part of your comment, I'm very interested in the answer. I have no answer about this. Anti-Zeno effect is very interesting. But why do you think anti-Zeno effect occurs if you make measurement only half a system?
Yeah. So for example, we can consider collective operators which is constructed of such each site operators. So like just like bell state measurement. So bell state usually operates in two sides only, but you may consider large coherent collective measurement operator for the half part of the system. And you can repeatedly perform such a semi-non-local measurement operator to the half system. Then I expect some kind of anti-zero effect. Just as a guess, I do not know the exact answer, but this is just a guess.
But even for the measurement only for the half a system,
yes.
The half a system may show the Zen effect. So the half a system measured system is projected onto the product state.
But
so
after,
not
I agree about that. But the point is a post-measurement state. Okay, so if you take such a project measurement for each site, then post-measurement state is a very low entangled state, right? Almost a separated state. So almost zero entanglement entropy. But if you have such a non-local operator for the measurement, then the post-measurement state becomes a more entangled state. So such an entanglement already yielded by the measurement, and this entanglement can be easily propagated to the other side of the system. So then,
I get the point. You want to introduce another type of measurement.
Yes, yes,
measurement.
yes,
yes.
yes.
It may be possible. Very interesting. Yeah, from time to time, I thought about the anti-Zeno effect. May occur or not, but this direction may be interesting.
Okay. Okay. Anyway, thank you very much.
Thank you very much for your comment. Very interesting.
Okay, is there any other question or comment? Maybe some people raise their hand button. Is there any other question or comment?
Can I ask a question?
Yes, sure, please.
Well, I have two questions. First one is in your second talk, I think you raised something lambda role for entanglement growth.
Oh, yes.
Yeah, here. And is there any interpretation on lambda role? What is this one?
Yeah, this is a very formal expression of entanglement growth rate. And if we start with the product state, this is the order one, then actually originally this enters HAV here, and we put the norm operator norm of HAV here and divided by operator norm here, and then this is the order one. And so if we start with the product state, then this should be small compared to the operator norm of HAP. Then we separate this contribution and this contribution. And so these are kind of artificial. So so nothing more than this consideration.
So why does the commutator appear here?
Because this is given by the time evolution. Any time evolution given by the Heisenberg equation.
And so far, you don't find any operational interpretation of this lambda rule.
At the moment, I have no interpretation about this.
I see. Okay, thank you. And my second question is about the measurement-induced phase transition. And in your talk, I think you assumed a projective measurement.
Yes.
And is it changing the frequency of the projective measurement is almost equivalent to the changing the strength of measurement, or maybe they are totally different?
I don't know your question. Actually, I don't understand what
Oh, well,
you
I meant by strength of interaction, like weak measurement.
Ah, okay. So that's another interesting question. It's not equivalent. I don't think it's equivalent because as already question is raised, the measurement in this patient maybe depends on the kind of the measurement. So the weak measurement, kind of weak measurement may show another effect. So actually, I don't know exactly about this, but the frequency is sorry, I don't know. I cannot answer correctly to your question.
I see. Well, is there any studies on such a changing the condition for the measurement?
Yes. Yeah, I remember several papers exist about the weak kind of a weak measurement, but I didn't read seriously about this.
I see. Oh, thank you so much.
Thank you very much.
So is there any quick question? Our time is already up, so if you have some quick question, please.
Sorry, can I ask a question?
Yes, sure.
So this, I mean, so to see the dependence of alpha by looking at this measurement induced phase transition is quite beautiful, I think. But also, can we see this alpha dependence from just calculating time evolution of entanglement entropy? So how it grows under time evolution without doing any measurement?
Okay, that is the fundamental question. There is a theorem about the upper bound of the entanglement growth rate. This is called SIE theorem. So just wait. SIE theorem. This is a small increment entanglement theory. This given by first latte. This means entanglement growth is upper bounded by gamma, some gamma, and gamma is given by C constant term times so I need to charge my Apple Pen. C H A B and logarithmic D. D is the minimum of Hilbert space of Hilbert space of A or B. But this is very well known upper bound of the entanglement growth. So one of your question is about the entanglement growth of the pure quantum dynamics. And another question from your question is that is there any relation between the entanglement growth and the phase transition?
So actually, I'm just without doing any measurement. So I think entanglement growth also depends on alpha.
Yes.
I just wanted to know how.
Yes, from this formula, we can estimate the, at least we can estimate the upper bound of the entanglement growth. And this depends on from this criteria, from this theorem, we can estimate the operator norm of HAB, and we can estimate the alpha dependence of the HAB. Then like this, we can estimate the entanglement growth rate in terms of the exponent alpha.
I see. Yes.
So in that case, you can prove that there is a linear growth, at most linear growth when alpha is large enough, satisfying your sufficient conditions, right?
Linear growth in time, or?
Yes. Because its dot is upper bounded by a constant, at least initially. Is it true?
Near initial time, you mean?
Yeah.
Yeah, at least in linear initial time, near initial time, you can show the linear growth. Yes.
But what do you have when this the norm of HAB is infinite? Do you see sharp increase or something much more weird?
Yeah, I don't know, because this is a bound.
Oh, right. Of course.
I don't know.
Yeah. You don't know.
Highly depends on the system you are looking at.
Oh, but you have simulation. You mean you can run your simulation without measuring, then you will get an answer. Yeah.
Yes, of course, yes. That's interesting. Yes.
It can have maybe some exponential growth.
Yes.
For alpha.
I think so. Yes, but yeah, there are several papers about this. This indicates the fast scrambling in the OTOC also. Entanglement also exponential growth, and scrambling also observed.
Thank you very much.
But yeah, I don't remember much about this.
Okay, thanks. So is there any quick question? If not, let me close question time. So thank you very much for great talk, Saito-san. Again.
Thank you very much.
So anyway, we can discuss something in the special chat, which will be open after this Zoom. I think you can find the address on the chat box in this Zoom. So please visit it if you are interested. So thank you very much again.